So now we're going to look at the contents of what we're going to cover in this subject. So we're going to cover the airframe of the aircraft engine itself and its components, carburetor, aircraft systems, so how they all work, and instrumentation. Okay, and all these will be covered in more detail, which is applicable to the PPL syllabus for the exams. So the major components of an aeroplane are the fuselage, which is the main body where the passengers sit, the wings, which create the lift, tail assembly, which is the horizontal and vertical stabilizer, flight controls, so how we maneuver the aircraft, the landing gear, which absorbs the weight of the aircraft, and the engine and the propeller. Okay, so we're going to go through all of these in more detail. First of all though, we're going to look at the fuselage, so the main body of the aircraft, and it is the main structure to which all other components are attached. Okay, so all the other components are attached to the fuselage. So the fuselage is the main part of that. Now, different aircraft have different construction techniques, but most light aircraft are of a semi-monocoque construction, and we'll go through what that means next. So first of all, what is a monocoque construction? And a monocoque construction is when the skin of that structure is the entire weight-bearing structure. So the skin has all the strength in it to hold a shape the way it is. Okay? There are formers inside used to keep the shape, but they aren't structural bearing. It's the skin itself that holds the weight of the aircraft and its strength effectively. So an example of this maybe could be something like an egg. If you were to hold an egg and squeeze it really hard, it's probably unlikely to break, but once that shell cracks, then the structural integrity of the egg is broken, and that's similar to a monocoque construction where the skin holds all the rigidity and the strength within the structure. And then we have a semi-monocoque construction. Okay, so the way this works is there's a lightweight framework inside which supports the skin, and it's the combination of the framework and the skin itself which will give the structure strength. Okay, so it's a combination between formers and skin that improves the strength of any structure. If the skin is damaged, that means that not necessarily the whole structure will be compromised in strength, as it's got sort of almost two layers of protectivity. And most aircraft make use of this technique as it offers the most redundancy if anything were to get damaged. So next we're going to look at the wings. So the wings itself are the component that create lift, and they're exposed to very heavy loads. And those loads are well in excess of the aircraft's weight itself. The main structure of the wing is a central spar, which is where all the strength within the wing lies. Okay, and it carries the loads vertically, upwards and downwards. And then from the spar there's also ribs, which often stiffen the skin of the wing itself, and they help transfer some of the load, so it just increases the structural integrity of the aircraft. So again, here's a diagram of a wing construction. So you've got the skin itself, which offers some strength. We've got the main spar, which is the most load-bearing part, and then the ribs itself, which offer some strength in a perpendicular direction. Okay, and all of these together is what increases the strength within the aircraft. So different aircraft have different wing designs, and it's by and large to their purpose. Okay, so you can see that some aircraft have a lower wing, some aircraft have a higher wing, or some aircraft have a biplane design, so dual wings. Okay, they all perform the same purpose, and it will have very slight characteristic differences between the handling of these aircraft, but by and large they all perform exactly the same in terms of creating lift. It's just a different way of constructing an aircraft. So next we're going to look at the tail, or otherwise known as the empennage. and it consists of two elements. Okay, we got horizontal stabilizer and a vertical stabilizer. Okay, most conventional is the horizontal stabilizer lower down with a vertical stabilizer going up, and it's better because it's easily accessible for checking on the ground, but it's more susceptible from turbulence from the wings. There are also T-tail designs where the horizontal stabilizer is higher up, and that means it's clear of that turbulence, so it's slightly smoother to control. However, it's inaccessible on the ground, so it's harder to check for damage on the pre-flights, and also a high T-tail design is susceptible to a steep stall, which is talked about in Principles of Flight. So just some housekeeping about securing an aircraft. So we want to secure the aircraft facing into the wind if possible. We should tie it down as well if we can, so tie it to the floor to make sure it's not going to move around. We want to lock the control surfaces, and that's locked within the aircraft, which means the control surfaces aren't free to move around. Covering the pitot tube with a cover, as well as in all engine openings, and we'll talk about some of these elements later on in AGK. And if in any doubt, just refer to the pilot's handbook, where it will give the best way to do all of these things. So next we're going to look at cabin ventilation, so how the cockpit of the aircraft gets ventilated with warm and cooler air. So for cooler air, there's normally a vent which just opens up to the outside where fresh airflow can flow into the cockpits, providing the cooler air from the outside inside the cabin. Warm air, however, is obviously much harder to come by, and it's taken from around the engine, so there's a shroud around the exhaust, and that air is heated by the exhaust, which is then pumped into the cabin as hot air. Okay, we just need to be careful that because it's taken from around the exhaust, if there was any pipes damaged in regards to the exhaust, then that exhaust gas could leak into the air ventilation system and therefore cause carbon monoxide poisoning, which can be deadly if exposed to. Okay, and that's why we have carbon monoxide poisoners, which we'll look at next. So it's just being aware that all the hot air is coming from around the engine and the gases associated with that. So as I said, carbon monoxide poisoning could be present if there's a leak in the exhaust system and therefore the ventilation. So we just need to be aware of it. We talk more about it in Human Performance and Limitations, but some of the symptoms could be a headache, dizziness, nausea, a deterioration of vision, slow breathing, unconsciousness, and eventually, if we don't do anything about it, death. Okay, so we do need to be aware of it. If we start experiencing some of these symptoms, we want to open the cabin air vents and let that fresh air from the outside come in, so we're not exposed to much of that hot air, which could possibly have carbon monoxide poisoning in it. We also have detectors in the aircraft in two forms. One is an alarm, just like a fire alarm, and also we have this one as well, which is a orange circle. And once carbon monoxide has been detected, that orange circle will start to get some black dots on it. So now we're going to look at an aircraft engine, okay, and more specific to the kind of engines that we will be using, which are piston engines. So we'll look at different kinds we get and what we'll actually be using in the aircraft we fly. There's lots of different types of piston engine aircraft, so different the way they're built and their purposes. However, most engines in general aviation are horizontally opposed, and we'll look at that slightly later on. And normally engines for aviation are specifically designed. They have higher tolerances, they're generally stronger, lighter to save weights, and they have more reliability. So the first engine we're going to look at is a radial engine. And the cylinders in a radial engine are arranged around a central crankshaft. So they're all the way around a central point. They're quite large in diameter. And what this does is it allows for a high number of cylinders in a small space. Okay, so they've got high power to size. Generally, they're quite complex and they're quite prone to malfunction. They're generally found on older aircraft. They're not yet used too much nowadays, but they do output a lot of power, which is why they were used some years ago. The next kind of engine is a straight 4. So instead of being horizontally opposed, it's vertically opposed. It's very simple design. It's easy to access all the certain parts of the engine. However, it's not very space efficient. So it's quite large in size. There's a lot of wasted space underneath the cowling, and they are ultimately a little bit heavier than the engines that we use nowadays. And these will be generally found on smaller but older aircraft. So we also have diesel engines, and these are very modern engines, the way that they're produced. However, they run off diesel or more commonly jet A1 fuel. And the advantage of this is a lot cheaper to run. It's a lot cheaper fuel. It's a lot stronger as well, and they're often based off car engines, which are then adapted for aviation. However, the disadvantage with this is they do require heavy turbochargers to give it that extra power. So they're generally a heavier engine, but then they are more reliable and cheaper to run an aircraft on as well. So more commonly, what will be used is a horizontally opposed. So that means the cylinders will be moving in a horizontal direction, and normally a 4-cylinder or possibly a 6-cylinder on the aircraft. And this is the most common type of engine. It's very lightweight, it's simple, and that's what is the best for aviation, to save weight and to make it easy to maintain. So now we're going to look at the piston engine in a bit more detail, as you need to know it for the CAA exam and how it works and all the elements to it. But the main purpose of the cylinder or the cylinder piston engine is to create chemical energy, so petrol or fuel, into kinetic energy, so into a energy that we can use. The crankshaft, which is the central point of the engine, and the connecting rod, which connects the cylinder and the piston, converts horizontal motion into a rotary motion. So that's what the cylinders are horizontally opposed within a piston engine, and the crankshaft will turn that horizontal motion into a rotary motion to turn a propeller or some kind of drive shaft. So we need to look at the stages of a 4-stroke cylinder engine, also known as the Otto cycle. And there's 4 main stages you need to know. Now, in a 4-cylinder engine, these won't all happen at the same time. They all happen simultaneously. So one cylinder will be doing one event, the other cylinder will be doing another. Okay. So the first stage is called the intake stage. Now that's where there's 2 valves. There's got an inlet valve where air-fuel mixture comes in, and then we got an exhaust valve. And you can see those on the first number 1 picture. There's those 2 sort of T-looking shapes. The inlet valve is the top one. The exhaust valve is the bottom one. We've also got 2 magnetos as well, which are those things on the side of the cylinder wall. And then we've got the piston head, the con rod, and the crankshaft lower down.